Welcome back to Chapter 14, Glycolysis, Gluconeogenesis, and the pentose phosphate pathway. In this lecture, we will discuss part 2 of this chapter, which deals with the payoff phase. In part 1 of this chapter, we discussed the preparatory phase of glycolysis. In this phase, the cell invests 2 ATP molecules in a series of reactions which involves the conversion of glucose to 2 glyceraldehyde 3-phosphate molecules. Although the overall delta G0, or the standard free energy change, is 2.1 kilojoules per moles, the reaction going from step 5 to step 6 proceeds because the cell keeps the concentration of glyceraldehyde 3-phosphate low at all times, and hence the actual free energy change is negative. Let us enter the payoff phase, step 6 of glycolysis. Step 6 of glycolysis involves the conversion of glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. This reaction is catalyzed by the enzyme glyceraldehyde 3-phosphate dehydrogenase, or GAPDH. This enzyme uses inorganic phosphate as another reactant and NAD+ as a cofactor. The rationale for this reaction is the generation of a high-energy phosphate compound. 1,3-bisphosphoglycerate is a high-energy phosphate compound. Incorporation of inorganic phosphate. Inorganic phosphate can be used as a reactant, and inorganic phosphate is found everywhere and is free floating and can be utilized by this enzyme, which is a big deal. Allows for net production of ATP via glycolysis. Again, this reaction sets the stage for the production of ATP in further steps. First energy yielding step in glycolysis. So this happens to be the first energy yielding step, which means that it sets the stage for the payoff. Other important points being the oxidation of aldehyde with NAD+ gives NADH. So the aldehyde is oxidized to this phosphoglycerate molecule, and in this process, NAD+ is reduced to NADH. There is an active site cysteine which acts as a nucleophile in the enzyme glyceraldehyde 3-phosphate dehydrogenase. It forms a high-energy thioester intermediate, and it is subject to inactivation by oxidative stress as well. Now, if you look at the standard free energy change, it is thermodynamically unfavorable or reversible. And one of the ways in which this reaction proceeds forward is by coupling to the next reaction. Shown here is the mechanism of GAPDH reaction. As I said, this enzyme has a nucleophilic cysteine in its active site. Now, shown here is the active site of GAPDH, and this is where NAD+ binds, and the substrate binds here. Once the substrate binds and forms an enzyme substrate complex, the nucleophilic thiolate anion attacks the carbonyl carbon of the aldehyde, and this polarizes the carbonyl bond, and the electrons are moved towards the oxygen. Once this bond is formed, the electrons and oxygen move back to the carbonyl CO bond, and that results in the loss of a hydride. Now, as you can see, H is lost as a hydride. It's not a proton, it's a hydride. So it's an H- that is getting lost. At the same time, an electron pair is being transferred to NAD+. And as a result, NAD+ becomes NADH. And results in the formation of an enzyme substrate intermediate. and this is a thioacetyl intermediate. Once this is formed, NADH leaves and phosphate is bound, and the phosphate O minus attacks this carbonyl carbon of the thioacyl enzyme intermediate. And once this happens, the leaving group, which is this cysteine, leaves, leaving behind 1,3-bisphosphoglycerate. This then exits the enzyme, and the product is thus obtained. Step 7 of glycolysis. Step 7 of glycolysis involves the conversion of 1,3-bisphosphoglycerate to 3-phosphoglycerate. And this is the first step in glycolysis that involves the production of ATP. And this is catalyzed by the enzyme phosphoglycerate kinase. And it uses magnesium as a cofactor, which binds ADP and results in ATP. The rationale for this reaction is that it's substrate level phosphorylation to make ATP, the first step in glycolysis, that pays off. 1,3-bisphosphoglycerate is a high energy compound. 1,3-bisphosphoglycerate is a high energy compound and can donate the phosphate group to ADP to make ATP. So it has so much energy that it can donate the phosphate to ADP to make ATP. And yet the standard free energy change is minus 18.8 kilojoules per mole. Kinases, as you may remember, are enzymes that transfer phosphate groups between ATP and various substrates. As I said, this is highly thermodynamically favorable and reversible. It's reversible because of coupling to GAPDH reaction. Step 8 involves the conversion of 3-phosphoglycerate to 2-phosphoglycerate. And this is catalyzed by the enzyme phosphoglycerate mutase. Now, this reaction is, again, an isomerization reaction, wherein this phosphate from the 3-hydroxy, or the hydroxy at the 3 carbon, to the hydroxy at the 2 carbon. This reaction may look a little bizarre as to why would cell want to remove a phosphate from a primary hydroxy and put it on a secondary hydroxy. The rationale: to be able to form high energy phosphate compound, mutases catalyze the migration of functional groups. And it is apparent here is that the functional group is phosphate, that is going from attached to the hydroxy of 3 carbon to the hydroxy of the 2 carbon in phosphoglycerate. One of the active site histidine residue is post-translationally modified to phosphohistidine. This is an interesting reaction, and it is worth noting that this is not a usual reaction and is unusual in many cases. Thermodynamically unfavorable because of the positive standard free energy change. Reactant concentration is kept high by phosphoglycerate kinase to push the reaction forward. So remember, here the reactant concentration is kept high. It is worth understanding the mechanism of the reaction catalyzed by phosphoglycerate mutase because it is unusual. And it is unusual because the enzyme has 2 histidine in its active site, and one of them happens to be attached to a phosphate group, and it exists as phosphohistidine. When the substrate 3-phosphoglycerate binds the enzyme and it forms an enzyme substrate complex, one of the histidine that is not phosphorylated abstracts a proton of the hydroxyl group at the 2 carbon from 3-phosphoglycerate. And once it happens, it becomes an anion, and that anion attacks the phosphate that is attached to the histidine in the active site of phosphoglycerate mutase. As a result, a compound named 2,3-bisphosphoglycerate is formed, which has two phosphates. Now, the next step is the transfer of the phosphate group that is originally attached to 3-phosphoglycerate, that is the blue colored one. The histidine that was originally phosphorylated, which is now not phosphorylated, takes up that phosphate by attacking the phosphate center, and the O- that results abstracts a proton from the histidine that is not phosphorylated in the active site. This results in the formation of 2-phosphoglycerate. And now, as you can see, the phosphate has transferred from 3-hydroxy at the 3 carbon to the hydroxy at the 2 carbon. And for this reaction to happen, the enzyme needs to have a histidine that is phosphorylated at all times. Hence, the unusual mechanism. Step 9 of glycolysis involves the conversion of 2-phosphoglycerate to phosphoenol pyruvate. And this is catalyzed by the enzyme enolase. And what is happening in this reaction is a dehydration reaction. Water leaves, resulting in the formation of this alkene compound. The rationale is to generate a high-energy phosphate compound. Phosphoenol pyruvate is the high-energy phosphate compound. 2-phosphoglycerate is not a good enough phosphate donor to generate ATP, and hence need to be converted to phosphoenol pyruvate. Two negative charges in 2-phosphoglycerate are fairly close. That is the first reason. The second reason is the loss of phosphate from 2-phosphoglycerate would give a secondary alcohol with no further stabilization. So if you remove the phosphate, because there is repulsion between the anions that are next to each other, you will not get a compound that has further stabilization. Only if you remove a water molecule and get a phosphoenol pyruvate compound, you will have further stabilization due to resonance. And that is the reason for this step to happen. Furthermore, this reaction is slightly thermodynamically unfavorable and reversible. For this reaction to go forward, the product concentration is kept low so that it can happen. Another thing to consider is the reason why 3-phosphoglycerate is converted to 2-phosphoglycerate. And it is specifically so that 2-phosphoglycerate can be converted to phosphoenol pyruvate, because phosphoenol pyruvate can only be obtained by 2-phosphoglycerate from 2-phosphoglycerate. Step 10 of glycolysis. Step 10 involves the conversion of phosphoenol pyruvate to pyruvate. And this is catalyzed by the enzyme pyruvate kinase. Pyruvate kinase uses magnesium cofactor and ADP and transfers the phosphate from phosphoenol pyruvate to ADP, resulting in the formation of ATP. The rationale for this reaction is a substrate level phosphorylation to make ATP. Net production of 2 ATP per glucose molecule. The reason 2 ATP is because there are 2 phosphoenol pyruvate molecules that go through this route, because 2 glyceraldehyde 3-phosphate molecules is obtained from 1 glucose molecule. Loss of phosphate from phosphoenol pyruvate yields an enol that tautomerizes into a ketone. Now, the tautomerization is shown here. This is the tautomer that of pyruvate in enol form and pyruvate in keto form, as you can see. This tautomerization effectively lowers the concentration of the reaction product. This is the product of the reaction, and once this is formed, it tautomerizes to form pyruvate, and hence the concentration of the reactant or the product is kept low. This drives the reaction towards ATP formation. More importantly, pyruvate kinase requires divalent metals, magnesium or manganese, for activity, and it is highly thermodynamically favorable and irreversible, as can be seen from its standard free energy change, minus 31.4 kilojoules per moles, even though it makes an ATP. It is regulated by ATP, divalent metals, and other metabolites. This slide shows the free energy changes of glycolytic reactions in erythrocytes. Thermodynamically unfavorable reactions are kept near equilibrium by sequestration of products. Overall process is driven by three highly favorable reactions. These reactions are highly regulated, and these three reactions are shown in red: the first step, the third step, and the 10th step. As you can see, all three of these red colored reactions have a fairly high negative delta G, which is the actual free energy change. And this is how glycolysis is controlled. And it is controlled mainly by regulating the metabolic flux of these metabolites. So, if you look at the summary of glycolysis, this is what happens. Glucose, in presence of 2 NAD plus and 2 ADP, 2 phosphate, results in 2 pyruvate molecules, 2 NADH, and 2 ATP. Now, what is not shown here, because this is the net reaction, what is not shown here is that 2 ATP molecules and 1 glucose molecule and 2 NAD plus are invested. And in return, what you get is 2 pyruvate molecules, 4 ATP molecules, and 2 NADH molecules. ATP molecules are used for energy requiring process within the cell. The pyruvates have various different fates. We'll talk about them in further lectures. NADH must be reoxidized to NAD plus in order for glycolysis to continue. But as I said before, NADH is equivalent to 2.5 ATP. That means that every NADH cell generates is a source of energy. In addition, glycolysis is heavily regulated. It ensures proper use of nutrients and ensures production of ATP only when needed. Before we end, I want to remind you one more time that the net energy production from glycolysis is 2 ATP molecules and 2 NADH molecules. How did we get it? We subtract this 4 ATP plus 2 NADH minus 2 ATP plus 2 NAD plus. NAD plus is not considered here because NADH is the ATP equivalent. So you get 2 ATP and 2 NADH. 2 NADH stands for 5 ATP molecules plus 2 ATP, that is 7 ATP is the overall yield. In ATP equivalence, if we consider and convert NADH to ATP equivalence.